speaker, Samsa van Hatterlo. Samsa is a clinical neurophysiologist and professor and senior consultant at Helsinki University Hospital in Finland, and he also leads the Baba Center in Helsinki. For the last 15 or so years, he's been working on the development of EEG hardware and other devices, and also doing mathematical signal analysis, neurobiological models for EEG activity. More recently, Samsa has started to develop wearable devices to assess infant sleep and mobility. And that's what he's going to talk to us about today. Thank you, Samsa.
Yeah, thank you, Kirsten. I hope you can all see this, can you?
Yes, we can see your screen.
Oh, very good. So good morning, everybody, from the very cold and still a bit gloomy settings in up here. I was very happy to have get this invitation from Rosa and colleagues, because I think we have been working on something that might be useful for many of us, or even most of us. It might even change the way how we do our clinical research, especially our research on early therapeutics. And it's actually all about wearables. So how can we use wearable technology for babies, and what's the real promise in that area? And as we all know, it's a field where it's a lot of activity. If you go Googling infant wearable, you get 155 million hits. It's a bit too much. And you put neurology, in addition, you get 11 million. And then you put neurodevelopmental, and you still get 300,000 hits. And of course, almost none of that is relevant in our context. But still, that's what you have in the internet. And what's our context then? It's all about trying to understand the early neurodevelopment, which in practice means that we want to understand the motility, because that's mostly about what the babies are doing. And then the real troubles actually begin in as far as what to do diagnostically. And as you all may be much better aware than I am, there are very nice guidelines and reviews and overviews and everything currently about the methods that we have at hand, so how they could be used for early prediction at least, and maybe also for early intervention. And in a nutshell, what they are telling us is that you need to put together a triplet. You need to have the standardized neurological examination. Then you might want to have the GMs, and then also add MRI imaging. And the nice thing is that these all are very widely known. But the downside actually is that they need a lot of expertise. They also need resources, and they mostly are qualitative, apart from MRI maybe. And there's also another downside, that there's limited information about the utility in lower risk infants, which actually is the main clinical group that we are facing in our everyday life. However, there's some indications that at least some of these measures might be even useful for other than predicting CP. And this is a nice work from a European consortium showing that if you take Hammersmith infant neurological exam, you repeat that over time during the first year. And here are examples from 6 and 12 months. The output on the score you get out of the exam has a correlation with the 2-year Bailey scores. So that means that there's something in the neurological performance that you can measure, and that is predictive of later more neurocognitive outcomes, not only the CP. And the real clinical problem is actually exactly there, that every 10th child is at some risk, and the risks they might develop are so many. And how could we make any reasonable prediction of all of the others than the CP alone? And then you come back to what's the target, and what can we really try to assess. And this is my perception of that the target, that we're trying to understand the trajectory of the functional development. So trying to see what all things happen and how they happen at each time. And in an optimal case, we pretty well know how things should go up. But then you have a lot of kids where things start deviate at some point, and then you have the kids that actually deviate a lot, and they never develop even close to where the others are going. Now, if you look at these two first ones, green and the yellow, that's actually the interesting things. The yellow ones are the ones that we are trying to rehabilitate. I mean, there we know that there's potential to improve. But if we focus on the very late age, there's quite little to see. So the main difference between these two groups is somewhere in the middle, and it's about the trajectory. And what we quite often are doing is that we take a very early time point, like 3 months, like GMs, and it's easy to understand that there's not much that has developed in as far as the difference between the groups. Or we might take very late time points when you don't see much between the fairly well-doing babies, but you will be able to pick up the worst ones. Or some other people are trying to pick some point in the middle, and then if you're very lucky, you might see a difference, but you don't. Then you are actually compromising your ability due to the quite wide variance between these individuals and between these trajectories. So what we are trying to propose is that why don't we take the whole thing? Why don't we try to look at the whole trajectory? And then the question is that really possible? And what would it take? This is how we view that. You need to have a measure that must be quantitative, it must be accurate enough, and it must suit a wide range of ages. It's quite something to do. And that's where wearables might have a solution. And then the question is that what can you measure with wearables? Well, in practice, you can measure almost everything, but not at all everything is very useful. And in our context, we're trying to understand the movement, because obviously, I mean, that's something that must be telling us something about the development. But then the trouble is that the babies are moving so much, and they don't follow our commands, or they don't do what we would like them to do. And there's studies showing that babies are changing their position every 10 to 20 seconds. So it's almost impossible to keep track of that without a constant surveillance. Now, solution to that is MAIJU, motor assessment in infants with a JUmpsuit, which means that you take a JUmpsuit, an overall, then you put sensors into the sleeves, then you have phone that collects the data, and then you have analytics. And the protocol, how we do it nowadays, is that we put the MAIJU suit on the infant, they go home, the suit comes back next day in a taxi, and then we have an algorithm to analyze the recordings. And what you get out is from this AI analysis is two time series, 2 streams. You get information for every 2-second epochs about the poster, 8 different kinds of posters of the baby, plus the type of movement of the baby. So these 2 informations, and then out of those you can do a lot of further analysis, like you can do summary metrics, you can quantitate things like how much they're sitting or how much they're walking in this and that way, and so on. Then the question is that why is to do it so complicated? Because people have been doing using accelerometers for 20 years or so. And the reason is quite simple. And that is very nicely shown by Beth Smith and their lab in LA some years ago. If you look at the amount of movement that you get, the only thing you get out of the accelerometer is, you can see that when you plot that against the age, the amount of movement doesn't really change. And this can be analyzed in many different ways, but in a nutshell, the accelerometer-based information has very limited relevance for understanding neurodevelopment. And this is an example from real life. Remember that the babies are doing different things all the time. So these are recordings, 24 signals that come out of the suit, 1,000 points every second. If you look at the blue labels, they show the the position of the poster of the baby, and the red labels show what the babies are doing. So even within this very short period, there's a large number of things, different activities that the baby is doing. And there's no real way to really map them up if you don't have this kind of signal collection. And what we have shown so far is that MAIJU is able to classify the poster and the movement at the reliability of a trained human observer. Meaning that you take a bunch of human observers, they watch the videos and label the video second by second and tell what the babies are doing. Then you compare that to the computer, and the computer agrees with the humans as much as the humans would agree with each other. That's about the ceiling, how far you can go. But of course, it takes quite some elaborated analytical algorithms in the background, but that's what we have trained over the past 2-3 years. And what's the potential gain? And these are 2 examples of where it could be used. And we have been playing, these are mock-up analysis, not published yet, but it shows some of the potential. So if you take an index of what you could call proficiency of the movement, and you plot that against the age over the whole cohort we have collected so far, there's a very strong correlation. So it shows that the JUmpsuit is able to show you the maturation of the baby. You can also look at the quality of the movements, and this is a sample of babies at 7 months of age, and the quality assessed from 1 to 3. And again, you look at the movement proficiency, so how mature they are, and there's a very strong correlation. And this same seems to repeat over and over. It doesn't almost matter what index you take out of the show. It very robustly correlates with age. So what's the take home? I would say that this solution is feasible, practical, and acceptable by the parents and the nurses and the babies. Can be used at home or anywhere, so it's really ecologically valid. It tracks spontaneous motility anywhere in a quantitative manner at very high accuracy. Allows you to track the maturation. And why to bother? And that's a good question. I think we have 3 prospects in mind. One is it obviously could be a great help in early diagnostics. It could allow to do neurodevelopmental follow-up even in the clinic. And maybe scientifically most exciting is that it could become an outcome measure in about any therapeutic trials. And this kind of work takes a lot of people. We have people from a technical side doing the recording technology analysis, textile engineering. Leena Hate is our child neurologist, and then I've been somewhere in the background. Then of course you need to have a lot of industrial partners to make this happen. And of course in the end, all we try to do is to understand the information the baby is trying to deliver us, like this young fellow is trying to tell us kiitos, which means thank you for the attention.